Gents, electrical and electronic principles at good old level 5. This module is going to run all year, so right through till mid-May and then exams. Okay. 4 learning outcomes. So number 1 is use circuit theorems to solve AC and DC circuits. I'm not going to read the whole lot out. So that learning outcome is a subject of exam paper 1. Yeah, so there's an examination on learning outcome 1. There's 2 exams and they are of an hour each. We'll come to where I'm going to put them in a little while. Okay. Number 2, use circuit design tools to design and test and evaluate the performance of 2-port attenuator and filter networks against designing computer model simulation. The lab report for those 2 designs is the subject of the assignment, and that's where we're going to start. So we're going to do the 2-port networks, have the lab sessions, get the assignment issued out of the way, well, not quite out of the way before we start on the other teaching stuff, but the practical side of it, and that'll become more obvious. You'll come in, you'll do your practical. Once the practical's done, you can then write your lab reports at your leisure at home, and we'll carry on with learning the other learning outcome 1. So they go in that kind of order. We'll do 2 first, then 1. 3, use Fourier series calculation techniques to analyse circuits involving complex waveforms. That's where you've got more than one frequency sine wave, for instance, added together to make a complex waveform. And then the last learning outcome is to use a mathematical technique called Laplace transforms to model the transient response. That's like the response at switch on or switch off when there's a change in a circuit you can use. And what that technique does is turn a calculus problem into an algebra problem. It's a little bit of a similar process like differentiating and integration. You actually move from one thing to another and then back again. It's like a mathematical process to simplify the analysis of transient response. So that those 3 and 4 are the subject of exam paper 2. Yeah. So the summary of the assessment is we've got 2 exam papers of an hour each and 1 assignment. The assignment is a lab report on learning outcome 2, attenuators and filters. Paper 1 exam covers learning outcome 1, circuit theorems, and then paper 2 covers learning outcomes 3 and 4, complex waves and Laplace transforms. Now, paper 2 will certainly be delivered in March, early June. So that's where that will go. That's that, and I've made up my mind about that. So that's the last part. Okay, and you'll have your definite exam dates either next week or the week after. I will have booked them. Sorry? May, early June. Beg your pardon. Keep you on your toes. If you're going to get them done by March, well, you'll be doing really well. Okay. Sorry about that. Paper 1, I've currently got in mind, I've penciled in to do paper 1 in the February half term. But I'm going to see how we do this week and next, possibly have it in the January Christmas break. Just think about how far we get. Well, if you think about it, we got 4 learning outcomes. We should really be getting 2 learning outcomes. If they're equal in content, we should be getting 2 done in semester 1, 2 done in semester 2. The thing that could hold it up, is that's quite a big group. If and when you're all here, there's 16 to get the practical work done. So there'll be 3 sessions, 3 weeks. Hopefully, if we need 3 weeks, where we'll extend an hour and a half beyond the project. The lab will be open and I'll be here for you to get that practical work done. And I won't get everybody to get it done on the first week, that's for sure. Okay, so that's the plan, and February is currently penciled in for exam paper 1, but we may get it done after Christmas. Alright? I'll make up my mind in the next couple of weeks. So, on to Learning Outcome 2 in its own right. Investigate the performance of two-port networks, design and test attenuator and filter circuits against a computer model. So you've got a single assignment and a lab report. So it's like a two-part lab report. We'll do one part on the attenuator, one part on the filter. And what this will be around is you have an A specification to design to. Yep. You design in a circuit using what's called preferred value components. So you can't get a 26 ohm resistor, but you can get a 27 or a 22. So you've got to pick which ones from the preferred values, simulate that design and see what the simulation software tells you the practical results is going to be, and then build the circuit and actually test the circuit and compare design with simulation with actual practical results. And you're doing that twice, once with the attenuator, once with the filter. You're going to use an online tool available freely from anywhere to do the calculations for the attenuator. We'll get to that perhaps later this week, if not next week. I'll show you that. And you're going to use a freely available program called ELSI to do your filter design and simulation. Alright, so those two things you'll be able to do away from here if you need to. One thing you may not be able to, unless where you work has got something like multi-sim or similar, is to do the multi-sim simulation of the attenuator. Okay, so that what I want to point out to you is when that's practical time, getting the things done you can't do at home is the important thing to do, because the rest of it you can do away from here with that free software. Alright? So then you're going to design a filter to a given specification as well and go through a similar process. So, this learning outcome's all about what's called two-port networks. So the basics. A two-port network takes an input, carries out some function upon it, and provides an output. So there we got an example there. An input port does a function and gives a result at the output port. Now that could be voltage reduction, attenuator. You're going to build one of them. Okay, 0 to 10 volt DC input, reduce the voltage by half, you get a 0 to 5 volt output across that range 0 to 10. So in this case, when this input is 10 volts, you get 5 out here. If the input is 5 volts, you get 2.5 out. It's going to attenuate by half across the range. Yeah. This example, have a change of signal, a two-port network that takes a 0 to 5 volt DC input and outputs a 4 to 20 milliamp signal. Okay? And in instrumentation you'll get various other kind of converters that will take a pressure signal and give you a voltage or milliamp output as well. Just out of interest, anyone involved in instrumentation, why generally go for 4 to 20 milliamp and not 0 to 20 milliamp? Yeah, well, not quite. The idea is that you've got a positive 0 value for current in that circuit. So if you've got nothing, you must have an open circuit because there's no current flowing. So it's a way of easily indicating that you've got an open circuit in that loop, because 0 is designated by a positive current. All right, and then This one, filter as a 2-port network, AC variable frequency input, and filter out all frequencies above 20 kilohertz. So we put lots of different frequencies in there, and all we get out are the ones above 20 kilohertz. 2-port networks. Okay? Everybody happy with that so far? Right, so our attenuators then. That's where we're going to start, with the attenuator. An attenuator is something that will reduce the level of a signal from a high value down to a selected lower one. And an attenuator has to fulfill 3 basic conditions. Number 1, have the correct input impedance, Zin. What that does is ensure the maximum power transfer from the source, which in this case might be your sensor. Think in terms of, let's imagine you've got a pressure sensor that gives you a signal, right? That'll have an output impedance, and we need to match that to the input impedance of the attenuator. More about that in a minute. Okay? It has to have the correct output impedance for the load you're going to connect to it. Again, that ensures you transfer the maximum power from the attenuator into the load. So that would be perhaps the pressure instrument. Okay? We'll come on to an example later, but if you imagine we've got a 0 to 10 volt sensor and our instrument requires 0 to 5 volts input, we can put an attenuator between the two to make that adjustment, to cut it down by a half. Okay? And then thirdly, and really the most important, is that it provides the correct attenuation level, i.e. if we want it to cut our voltage in half, it does that, and it does it across the possible range of inputs. So like the example I said, at 10 volts you got 5 out, at 5 volts you got 2.5 out, 2 volts you get 1 out. If it's a half attenuator, cut the signal in half. Alright? Now, the third condition is the reason for use of per resistance only. So we've got to have this as a caveat to specific attenuation level, and that is that it's independent of frequency. So attenuators only contain resistors, because resistors don't vary their value, their impedance value, with frequency. When we come to the filters, we start to include, in fact we include capacitors and inductors, because we want the attenuation level to vary with frequency. More about that later. Okay? So 3 main things: right input impedance, right output impedance, I'm going to explain that more fully in a minute, and the right attenuation level that is independent of frequency variation. And that's why we use Z, we use impedance rather than resistance here, because we're possibly talking about AC signals. Yep. So, this having the correct input impedance. What that means is, if we take the impedance looking into the source, so if this is our sensor, well, let's have a pressure sensor. We've got the impedance of the source looking in. Now that'll be specified in the information about the sensor. It'll tell you what its output impedance is. Okay? That, for correct input impedance, which we call, some people call matching, impedance matching, yeah, this impedance looking in to the attenuator with the load connected, the correct load connected, are the same, equal to each other. So if this is 50 ohms, then all of that, including the correct resistor for the load, right impedance, should measure 50 ohms as well for perfect matching. Yeah? Okay? Everyone happy with that? Or not? Then, correct output impedance means we take the impedance looking back into the output of the attenuator with the source device impedance connected. So that's a 50 ohm resistor, correct in our example. All of that, the impedance of all of that, is equal to the impedance of the instrument or other device you're going to connect to the output of the attenuator. Yep. And if you get that matching right, like I say, you transfer the maximum power from that source into the attenuator, and then from the attenuator out of there, and it keeps your attenuation level even right across the range of inputs. If you get that wrong, then you've got to get different attenuation levels, slightly different attenuation levels, dependent upon input. Okay? Everybody reasonably happy with that? And it does become a bit clearer once you start to have a go at designing. Yeah? So, attenuators. Different types. First of all, unbalanced attenuators. These are used where the signal is a voltage above or below a common rail. So for example, 0 volts common, 10 volts. Yeah. So we got a common line, and then we got a top rail. And then we can have what's called T-type, because they look like a T. Yeah, if you get an American textbook, they call them Y attenuators, okay? But we'll stick with that T. And these ones are called pi type because they look like the pi symbol to a certain extent. I didn't design the name and scheme, by the way, but anyway, T-type, pi type. Now, if you design for the same application an attenuator with T-type to one you designed with pi type, the component values will be different. Okay, I know of no real valid reason why you might choose one or the other for an attenuator, other than perhaps the availability of components or the amount of current that might flow and whether you've got resistors of the correct wattage rating to take the load. Okay, but you will get completely different component values if you change from a T-type to a pi type. And when you're given your specifications, some of you will have T, some of you will have pi's. Okay, but you're going to build an unbalanced attenuator with a 0 volt rail. Alright? You can also have balanced attenuators. Excuse me. This is where you have a signal that is a balanced signal, doesn't have a common, for example, plus 5 volts to minus 5 volts. What happens then is you design a T-type attenuator, and then you put half the series resistance in the top and half in the bottom rail, so you share that resistance between the two. So that's a T-type balanced, and that's a pi-type balanced. We share, again, half the series resistance top and bottom. And balanced signals are quite common in communication and such like, instrumentation signals, because if you have two rails plus and minus, if one gets interfered with, the other one gets interfered with, i.e. noise, in the same direction, and therefore the distance between them, the voltage between the two, is still the same. so they're less susceptible to noise if you used a balanced signal. Okay, but we're not going to build a balanced attenuator, we're going to build an unbalanced one. But for completeness, that's the other type. Okay, all your attenuators as well are going to have the same input and output impedance. Okay, so but you can have attenuators that have a different input and output impedance. They can be used to match two devices where the input and output impedance of the sensor is not the same as the input impedance of the instrument. But they get a little bit complex to get set up properly, and there are issues over them having a minimum design loss, i.e. you're always going to get some attenuation even if you didn't want any because of the matching. Okay, so we're going to build, or you're going to build, unbalanced, either a T or a pi type. Yep. So your attenuators are going to be what's called symmetrical, i.e. they have the same input and output impedance. For symmetrical attenuators, when you do your calculations, Z1 and Z3 in either design, so we've got the series resistors in the T type and the shunt or parallel resistors in the pi type, they will be of equal value. So if Z1's 100 ohms, Z3 will be 100 ohms, but Z2 will be different. Yep. And the same with the pi type. The single impedance that is both the input and output impedance is called the characteristic impedance, symboled ZO. Yep. So you're going to design, you'll be designing either a 50 ohm or 600 ohm characteristic impedance attenuator. Yep. They're used where the impedance of the source, the device you're connecting to the input, is the same as the impedance of the load device that you connect to the output. Alright? So, there's some methods that are used to calculate, if you wanted to, the characteristic impedance of a symmetrical T design. Your input impedance is the same as ZO, and your output impedance is ZO. We can calculate that by the square root of Z1 squared plus 2 times Z2 times Z1. Fairly simple calculation if you needed to do it, but unless you've got an attenuator sit there with 3 resistors and you want to know what the input and output impedance is, the characteristic impedance of that is, there's little reason to do that calculation. It's not a design calculation, that one, because you design by finding out what the component values are rather than what the input and output impedance of a set of component values are. So you design to an impedance and attenuation level. We'll come to that in a little while. And then the pi, again, through all of these calculations, including the manual ones for designing a attenuator to a particular design, the pi ones generally look more complex than the ones for T-type. Okay? But they aren't particularly difficult to do. They just look more complex. There seems to be more to them. So that calculation will give you the characteristics of a symmetrical pi type design. Yeah. And I'm not going to label those calculations too much, because they aren't ones that we need to do to design an attenuator to a particular value. Something you might want to do, though, is find the value of ZO of an attenuator that you've got in your hand you want to know what its input and output impedance are. There's no markings on the resistors. You've got no resistor values, so you can't do either of those two calculations we've just done. That could even be a black box where you can't see the component values inside it. You don't know if that's pi or t. Right? But regardless whether that's pi or t, what you can do is measure the input impedance with the output disconnected, i.e. find Z open circuit, and then short circuit the output and find Z short circuit, and then you can use that formula and it will tell you the ZO of your attenuator that you've got in your hand. Okay, so there's a kind of practical thing where you might want, a bit like in science, we identified the values, we used some techniques to identify the values of those capacitors and the inductor. There's quite often a practical way to find out the values of components and things about a circuit. Okay? There's a similar technique, short and open circuit values in a transformer to find out characteristics. If you come study with me at level 6, you'll have a go at that. So there's quite often a way of doing that practically. Okay, now attenuation factor or ratio. So these two-port networks and these attenuators have got a voltage in, for instance, and a voltage out. And if we do V out divided by V in, i.e. the voltage we get out divided by the voltage we put in, we end up with a gain on any two-port network. For an attenuator, V out divided by V in will be less than 1, and therefore it's a loss. It's an attenuation. So instead of a gain is normally associated with amplification. You get a 10 times gain or a 20 times gain. Okay? If you end up with a gain less than 1, a multiplier less than 1, it means you're actually reducing the signal. You're attenuating the signal. Okay? Equally, we could calculate the current or power gain or attenuation factor. Alright, the number of times we're reducing it by. So, depending on what we want to do with calculations, we need to consider either in terms of gain, in terms of attenuation, or attenuation factor. So, we need to consider how the industry measures gain and attenuation. In many cases of gain or loss, the numbers involved are very large or very small. Yeah? So an amplifier can easily have a gain of 100,000 or more. So, for convenience, it's better to use a logarithmic system. If logs to the base 10 are used, then the ratio is said to be in bells. This is a large unit, and it's more common to use the decibel, dB, where 10 decibels equals 1 bell. Right, so any of you not heard of the term decibel? You should have heard it in terms of sound levels and safety, if nothing else. Okay, but it's a measure of gain or attenuation in amplifier circuits. All right. Now, the important one is the power ratio in decibels. We get that by doing 10 times the log of the power out divided by the power in. And with these ratios in here, it's always the out over the in. So P out over P in gives us the power ratio in decibels. You're going to need, okay, to have, for the online calculator, you're going to need to specify your attenuation level in dB power. Yeah, but you'll only have specification that gives you voltage in and voltage out. So what you then need to get the power ratio is to substitute for P out V out squared over Z out. You remember? Power is V squared over Z. Yeah. Substitute in for P in, V in squared over Z in, and you'll get your power ratio from that. Okay. If you had current instead of voltage for your specification, you would substitute in I squared times Z, I out squared times Z, I in squared times Z. So you're going to need one of those for the assignment. So don't lose that, because you're going to need it. Alright? So, examples. If we had a P out over P in equal to 1, the dB ratio is 0. If you get your calculator out and do log of 0, log of 1, sorry, you should get nothing. Okay? Now, if you do log of 100, you should get 20 for your dB. You've got to put 10 log 100, sorry. 10 times the log of 2. Going back to the previous slide, it's 10 times the log of P out over P in. So that's 20 dB. Yeah. If you put in 10 times the log of 0.1, you get minus 10. Now, that's a gain of minus 10 dB. Yep. The proper way to describe it. Or an attenuation of plus 10 dB. Everybody get that? So negative gain is a positive attenuation. The calculator again requires you to strip that negative sign off and enter a positive attenuation level for your attenuator. Alright? If you're interested in voltage or current ratios, then you can get the current ratio in dB from 20 times the log of I out over I in, and you can get a voltage ratio from 20 times the log of V out over V in. Okay? A lot of upfront information in this part of the module, unfortunately. We'll have a go at some calcs in a minute. Okay? So, here we go. Problem definition. A pressure sensor produces a signal of 0 to 20 volts across its rated pressure range when connected to a load impedance of 500 ohms. You need to connect it to an instrument requiring an input voltage between 0 and 10 volts with an input impedance also of 500 ohms. So we're okay, we can do a symmetrical attenuator because both the ohm values, we've got a ZO here, yeah? But we need to drop the voltage by a half across the range. So we can achieve that with a passive attenuator made simply out of resistors.